Welcome, everyone. Thank you for being here today. I'm excited to introduce our presentation on forest fire. This is the first slide, the cover slide, so I want to warmly welcome you all and set the stage for what's to come. Today, we'll explore the causes, impacts, and ways to prevent forest fires. We'll also look at some recent examples and discuss strategies for managing these devastating events. Let's get started. Let's start by looking at the basic understanding of this fascinating phenomenon called combustion. Now, as you know, combustion is closely related to photosynthesis. During photosynthesis, plants take in carbon dioxide and water, and using solar energy, they produce glucose and oxygen. This process can be summarized as CO2 plus H2O plus solar energy yielding a carbohydrate, specifically C6H10O5N, along with oxygen. Now contrast that with combustion. When a substance like this carbohydrate, C6H10O5N, encounters oxygen and reaches a certain temperature, what we call the kindling temperature, it begins to burn. This process releases energy in the form of heat, along with carbon dioxide and water. What's interesting here is the role of that kindling temperature. It acts like a catalyst, really, because it's the point at which the ignition occurs. It helps initiate and sustain the combustion process. Without reaching this temperature, the reaction simply wouldn't start or continue efficiently. So, in essence, photosynthesis and combustion are two sides of the same coin. One captures energy from the sun to build molecules, and the other releases that stored energy through burning. This connection is fundamental to understanding energy flow in our environment. Now let's look at the first phase in the combustion of plant fuels, which is the preheating phase. During this stage, the plant material ahead of the flames is gradually heated up to its ignition point. This process is crucial because it prepares the material for combustion. In this phase, moisture within the plant material is driven off. That's why you'll often see steam or vapor during early heating. At the same time, the heat causes the generation of flammable hydrocarbon gases. These gases are important because they will later ignite and sustain the combustion process. Understanding this initial phase helps us see how plant fuels begin to burn, setting the stage for the more vigorous chemical reactions that follow. It's all about getting the material ready, making sure it reaches the right temperature, and releasing the gases that will fuel the fire. The ignition of these gases heralds the beginning of the second phase of combustion. This stage is characterized by flaming combustion, where you see visible flames as the gases burn actively. It's an exciting transition because it shows the combustion process in full, lively motion. Moving on to the third phase, the remaining charcoal is gradually consumed by glowing combustion. Here, the process is less intense but still vital, as it leaves behind a small amount of residual ash. Understanding these phases helps us see how combustion evolves and sustains itself over time, which is key to grasping the overall behavior of burning materials. Let's take a closer look at the different fuel types involved in combustion. Heavy fuels, which tend to have low flames, generally release more heat energy overall. However, this energy is released at a slower pace, mainly through glowing combustion. On the other hand, lighter fuels, such as grass material, tend to release most of their heat energy during flaming combustion. This distinction is important because it affects how quickly and intensely a fire can develop. Understanding these differences helps us better predict fire behavior and manage fire safety more effectively, which ties back to our overall goal of understanding fire dynamics and control. Now, let's explore the three different zones of fire. In the first zone, you'll notice that the leaves and other fine fuels start to curl and become scorched. This happens because of the preheating effect caused by the oncoming flames, which gradually prepares the fuels for combustion. Moving into the second zone, we encounter the flaming zone, where burning gases are actively ignited, producing the flames we commonly associate with fire. This is where the combustion process is most vigorous. Finally, there is the third zone, which is less obvious but equally important, the burning charcoal zone. Here, the charcoal continues to smolder and radiate heat, maintaining the fire even after the active flames have subsided. Understanding these zones helps us better grasp how fires spread and behave, which is essential for effective fire management and control. Let's talk about how heat energy transfers to the adjacent potential plant fuel. This happens through several processes: conduction, convection, radiation, and also through the movement of hot or burning plant material, which we often refer to as spotting. Spotting is when embers or burning pieces are carried by the wind to new areas, igniting fresh fuels. Now, apart from spotting, especially when we look at a moving fire front, the primary modes of heat transfer are convection and radiation. Convection involves the movement of hot air or gases, which transfer heat through fluid motion. Radiation, on the other hand, is the transfer of heat through electromagnetic waves, which can occur even through empty space. Understanding these heat transfer mechanisms is crucial because they directly influence how quickly a fire spreads and how effectively it ignites new fuels. So, whether it's through direct contact, the movement of hot gases, or radiant heat beams, these processes work together to drive the fire's progression across the landscape. Convection currents play a key role in how fire preheats the environment above the ground. They are mainly responsible for warming the higher shrub layers and the crowns of trees, which are often the most vulnerable parts of the forest during a fire. This preheating makes these fuels more combustible and easier to ignite. At the same time, radiation from the flames is another critical factor. It accounts for most of the preheating of the fuel ahead of the fire front. Essentially, the heat radiates outward from the flames, warming the fuels that are not yet in direct contact with the fire. This process helps the fire advance more quickly by preparing the fuel ahead, making it more likely to catch fire when the flames reach it. Connecting these points, understanding both convection and radiation helps us better grasp how fires spread through different layers of vegetation. It's a reminder of how fire behavior is influenced by multiple factors working together to preheat and ignite fuels, ultimately driving the fire's progression. Now let's take a closer look at the different types of fire. First, we have ground fire, which burns below the surface of the ground in deep layers of organic material. This type of fire can be quite insidious because it smolders underground, making it harder to detect and control. Next, there's surface fire, which is the most common type you'll encounter. It burns in the surface vegetation, such as grasses or undergrowth in wooded areas. Think of grass fires that spread quickly across grasslands or beneath the trees in forests. That's surface fire in action. Finally, we have crown fire, which burns in the canopies of trees and shrubs. This type can sometimes be independent of surface fires, meaning it can leap from tree to tree, moving swiftly through the treetops. Understanding these different types is crucial because each behaves differently and requires specific strategies for management and suppression. Connecting this to our overall theme, recognizing these fire types helps us better predict fire behavior and plan effective responses to protect our communities and natural landscapes. Fires can be further subdivided into different types based on how they burn and the direction of their progression. One common type is the head fire, which burns with the wind and tends to spread quickly because the wind pushes the flames forward. On the other hand, there's the back fire, which burns against the wind, moving more slowly and often used as a control method to contain larger fires. Understanding these distinctions is crucial because they influence how a fire behaves and how we manage it. Now, when we talk about fire behavior, one key parameter to consider is what influences fire intensity. That's essentially the amount of heat energy released per unit time and per unit area, so how hot and fierce the fire can get. Another important factor is the vertical distribution of that heat, often called the flame profile. This describes how the heat is spread vertically within the flames, which impacts how the fire interacts with the surrounding environment, including fuels and topography. By understanding these aspects, we can better predict fire behavior and develop more effective strategies for fire management and safety. Fire intensity is a critical concept in understanding how fires behave. It's essentially determined by two main factors: the amount of available heat energy and the rate at which that heat energy is released. When we talk about the amount of energy released, we're referring to how much heat is actually produced during combustion. This depends largely on the heat energy stored in the fuel itself. Now, this is where fuel load and the heat of combustion come into play. The fuel load is basically how much combustible material is available, and the heat of combustion, or more specifically, the heat yield per unit mass of fuel, tells us how much energy we can expect from burning a specific amount of that material. Understanding these relationships helps us grasp why some fires burn more intensely than others, and it's essential for predicting fire behavior. This knowledge connects directly to the overall theme of fire management and safety, as controlling the fuel and understanding heat release can influence how we approach fire suppression and prevention strategies. Now, let's talk about the amount of available heat energy at a given site. This essentially depends on two key factors: the fuel load and the heat of combustion. The fuel load is defined as the amount of fuel available for burning per unit area. That is, how much fuel is physically present in a specific space. The more fuel there is, the greater the potential heat energy that can be released. Then we have the heat of combustion, which is the total amount of heat energy released when a specific amount of fuel is burned. It's measured in kilojoules per kilogram or kJ per kg. This value tells us how much energy we can expect from each kilogram of fuel. Connecting this to our overall theme, understanding these factors helps us estimate the potential energy release at a site, which is crucial for managing fire behavior and planning effective responses. Essentially, the available heat energy is a product of how much fuel there is and how energy-rich that fuel is when burned. Let's talk about the rate of heat energy release during a fire. This is actually one of the most complex aspects of fire behavior to fully understand. It's not something that's straightforward to measure directly, which makes it a bit challenging for us. In practice, we usually estimate this rate by looking at how quickly the fire front moves forward. So, instead of measuring heat directly, we observe how fast the fire is spreading. This brings us to the term rate of spread. It describes how quickly the fire front advances over a given period of time. Understanding this rate is crucial because it helps us gauge the intensity and potential danger of a fire. Connecting this to the overall theme, knowing the rate of heat energy release and the rate of spread helps us better predict fire behavior, plan effective responses, and improve safety strategies. Now, let's talk about how we determine fire intensity. The key parameters we look at are heat yield, fuel mass, and rate of spread. These factors come together in a specific equation to give us an estimate of how intense a fire is. The equation is I equals H times W times R here. I represents the fire intensity, measured in kilojoules per second per meter. H is the heat yield of the fuel, which tells us how much energy is released when the fuel burns, measured in kilojoules per kilogram. W is the amount of available fuel per unit area, in kilograms per square meter. And R is the rate at which the fire front spreads, measured in meters per second. What's important to understand is that each of these parameters influences the overall fire behavior. A higher heat yield, more fuel, or a faster spread rate all contribute to a more intense fire. This formula helps us quantify that intensity, which is crucial for understanding fire dynamics and planning appropriate mitigation or response strategies. So, by analyzing these parameters together, we gain a clearer picture of the fire's potential impact and behavior across different environments. Let's take a closer look at how different types of fire behave, especially focusing on head and back fires. When we talk about the rate of heat energy release, it's important to understand that head fires tend to be much more intense than back fires. In fact, in the grasslands of the Eastern Cape, we see that head fires are roughly 7 times more intense than back fires. That's a significant difference and highlights how quickly and fiercely a head fire can spread. However, when we look at shrub communities, the gap between head and back fires isn't as wide, meaning the difference in fire intensity between these two types of fires is less pronounced. This suggests that the type of vegetation plays a role in fire behavior. Another key point is that head fires have a greater potential to reach higher maximum temperatures, provided the environmental conditions are right. This is crucial because higher temperatures can lead to more severe damage and faster fire spread. Understanding these differences helps us better predict fire behavior and develop more effective fire management strategies. It's all about recognizing how fire interacts with different landscapes and conditions to inform our responses. Let's take a look at the vertical distribution of heat energy in different types of fires. Ground fires, which burn the organic material beneath the surface litter, are characterized by glowing rather than flaming combustion. This means that the heat energy released during these fires is primarily distributed at and below the soil's surface, impacting the roots and organic layers directly beneath the ground. On the other hand, crown fires, which consume the foliage of trees and shrubs above the ground, tend to release a significant amount of heat energy at some distance above ground level. This distinction is important because it influences how heat spreads through the ecosystem and affects the potential for fire to spread vertically through different forest layers. Understanding these differences helps us see how fire behavior varies depending on the fire type and its vertical distribution of heat energy, key concepts in managing and predicting fire impacts in various landscapes. So, generally speaking, we can conclude that backfires tend to be more intense than head fires right at ground level. However, when we look at levels that are at or above the canopy of the grass sward, head fires actually become more intense overall. An important point to remember is that head fires are consistently hotter about 18 inches, or roughly 0.46 meters, above the soil surface. In contrast, backfires tend to be hotter below this level. This difference in temperature development relates to how much fuel is burning. Head fires develop more heat than backfires because more fuel is burned per unit of time in the head fire. Connecting this to the bigger picture, these variations in fire behavior at different levels are crucial for understanding fire spread and intensity, especially when planning fire management strategies. Let's talk about spotting. Spotting is essentially the beginning of a new fire, and it happens ahead of the main fire. This occurs when airborne firebrands or embers are carried by the wind and land in new areas. It's a critical process because these embers can ignite new fires far from the main blaze, making fire spread much more unpredictable and dangerous. The likelihood of spotting depends heavily on two key factors. First, the availability of firebrand material, that is, the amount of embers or burning debris that can be carried away. And second, it depends on how flammable the fine fuels are in the area where these embers land. Fine fuels like grasses, leaves, or small twigs are much more likely to catch fire from a single ember compared to larger, less flammable materials. It's also important to remember that not all vegetation types are equally prone to spotting. Some types are more susceptible because of their structure and fuel characteristics. Understanding which vegetation is more prone to spotting helps us assess fire behavior more accurately and plan our response strategies better. Connecting this to the overall theme, spotting shows just how complex and dynamic fire behavior can be. It's a reminder that fire can leap ahead in unpredictable ways, emphasizing the importance of understanding these processes for effective fire management and safety. Crown fires are generally more prone to spotting because of the greater availability of firebrand material in the form of fine branches, twigs, and sections of bark in the crowns of trees and shrubs. This means that when a crown fire occurs, there are more tiny, burning pieces that can be carried by the wind to ignite new spots ahead of the main fire. Spotting is a key factor in how quickly and unpredictably these fires can spread. On the other hand, spotting seldom happens during surface fires in grasslands and savannas. Why is that? Well, in these environments, the trees and shrubs are usually large and non-flammable, so they don't easily ignite and produce firebrands. Plus, the grasses burn so rapidly that there isn't enough time for burning embers to be transported over a significant distance before they burn out. So, the overall takeaway is that crown fires are more aggressive and harder to control because of their tendency to produce embers that can jump ahead, while surface fires in grasslands tend to stay more contained due to the nature of the fuels involved. This concept ties into our broader discussion on fire behavior and how different vegetation types influence fire spread. Now, let's talk about the factors that influence how much spotting occurs during a wildfire. First, the ease with which firebrands can be transported plays a big role. If firebrands can be carried easily by the wind or updrafts, they can ignite new spot fires far from the main blaze. Next, the flammability of the fine fuels where these firebrands land is crucial. If the ground or materials are highly flammable, even a small firebrand can start a new fire quickly. Increasing wind speeds also significantly affect spotting. The stronger the wind, the farther and faster the firebrands can travel. Steeper slopes are another factor. They tend to promote faster rates of fire spread, making spotting more likely and more intense. Lastly, the development of updrafts and convection currents within the fire environment helps lift and carry firebrands higher into the air. These currents can transport embers over long distances, creating new fires well ahead of the main fire front. All of these factors are interconnected and highlight how dynamic and complex spotting can be in wildfire behavior. Understanding these helps us better predict fire spread and improve our response strategies. Let's talk about some key factors that influence fire behavior, starting with fuel moisture. This refers to how wet or dry the available fuels are, and it plays a huge role in how easily a fire can ignite and spread. When fuels are dry, fires tend to be more intense and spread faster, whereas moist fuels can help slow or even stop a fire from taking hold. Next, we have air temperature. Higher temperatures often correlate with drier conditions overall, which can increase fire risk. Warm weather can also cause fuels to lose moisture more rapidly, making them more flammable. Relative humidity is another critical factor. It measures how much moisture is in the air relative to what the air can hold at a given temperature. Lower humidity levels mean drier air, which again fosters easier ignition and faster fire spread. When relative humidity drops, fuels dry out more quickly, elevating the fire risk. Then there's the period since the last rain occurred. The longer the time since the last significant rainfall, the drier the fuels become. This period allows the moisture content in fuels to decrease, making the environment more conducive to fire ignition and propagation. Connecting all these points, understanding these environmental conditions helps us assess fire danger more accurately. When fuels are dry, temperatures are high, humidity is low, and it's been a while since rain, the risk of a wildfire significantly increases. This awareness is vital for effective fire management and prevention strategies. Now, let's take a closer look at the factors that influence fire behavior. First up is the fuel factor. This refers to the type, amount, and arrangement of combustible materials available in a given area. The more abundant and easily ignitable the fuel, the more intense and rapidly spreading the fire can become. Next, we have atmospheric and physiographic conditions. These include whether elements like wind, temperature, and humidity, as well as the physical features of the landscape, such as slope and elevation. These factors can significantly affect how a fire starts, spreads, and intensifies. For example, strong winds can carry embers and increase fire spread, while steep slopes can cause fires to move uphill more quickly. Understanding these factors is crucial because they form the foundation of how we predict and manage fire behavior. When combined, fuel characteristics and environmental conditions help us assess fire risk and develop effective strategies for prevention and control. So, by paying close attention to these elements, we can better anticipate fire behavior and improve our response efforts. Let's take a closer look at fuel characteristics, which are essential for understanding fire behavior. First, particle size distribution plays a crucial role because it affects how quickly the fuel can ignite and how it burns. Smaller particles tend to ignite faster and burn more intensely, while larger pieces may smolder longer. Next, compaction is important because tightly packed fuels can limit airflow, influencing how the fire spreads and how hot it gets. Looser fuels, on the other hand, allow for better oxygen flow, making the fire more vigorous. Moisture content is another key factor. Higher moisture levels in the fuel slow down ignition and burning, while dry fuels ignite easily and burn more rapidly. This is why managing moisture is vital in fire prevention and suppression. Fuel load refers to the amount of combustible material in an area. The greater the fuel load, the more energy is available for the fire, potentially leading to more intense and longer-lasting fires. All of these factors, particle size, compaction, moisture content, and fuel load, interconnect to influence how a fire starts, spreads, and behaves. Understanding these characteristics helps us better predict fire behavior and develop effective management strategies. Let's talk about particle size and its role in fire behavior. Fine fuels include all plant material with a diameter of up to 6 millimeters. These fuels burn very readily because their small size allows them to ignite and spread flames quickly. This rapid ignition can lead to fast-moving fires, especially in areas with abundant fine fuels. On the other hand, heavy fuels are a different story. They consist of larger, bulkier materials, such as those found in forests, and combustion in heavy fuels tends to be incomplete. This is because the larger size and density of these fuels make it harder for the fire to penetrate and burn all of the material thoroughly. So, understanding the particle size helps us predict fire behavior, how quickly it spreads, and how intense it may become, and it's crucial for developing effective fire management strategies. Now, let's talk about fuel distribution. Fire behavior is heavily influenced by how plant fuels are arranged vertically. This means that where the fuels are located in the vertical space impacts how the fire spreads and behaves. One key aspect is ground fuels, which include all the combustible material below the loose surface litter. This can be decomposing plant material, roots, or other organic matter close to the soil's surface. These ground fuels are crucial because they support glowing combustion, often seen as ground fires. They are notoriously difficult to ignite initially, but once they do catch fire, they can be very persistent. This persistence makes them particularly tricky to manage because they can smolder underground for long periods, reigniting the surface fires later. Understanding this vertical distribution helps us predict fire behavior more accurately and develop better strategies for containment and suppression. It all ties back to the overall theme of how fuels influence fire dynamics and the importance of assessing fuel layers thoroughly. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about surface fuels. These include things like standing grass swards, shrublet communities, seedlings, forbs, and loose surface litter. Basically, all the fine fuels that sit on the surface of the ground. Now, these fuels are critical because they can support intense surface fires, and the key factor here is their quantity per unit area. The more of these fine fuels you have in a given area, the more likely you are to see a vigorous, high-intensity surface fire. This connection between the amount of surface fuels and fire behavior is essential for understanding fire risk and management. It really highlights how important it is to monitor and manage these surface fuels to prevent uncontrolled fires and protect our ecosystems. This slide doesn't contain enough information. That's why we're moving to the next slide. Aerial fuels refer to all the combustible material found in the upper parts of tree and shrub communities, both live and dead. This includes things like mosses, lichens, and epiphytes, as well as the branches and foliage of trees and shrubs. These fuels are particularly important because they can support very intense crown fires, which can spread rapidly through the canopy. Understanding aerial fuels is crucial in wildfire management because they play a significant role in how fires ignite and spread through forested areas. Recognizing the components that make up aerial fuels helps us better assess fire risks and develop effective strategies to protect communities and natural resources. This slide doesn't contain enough information. That's why we're moving to the next slide. Fuel compaction is all about how the individual pieces of fuel are arranged in relation to each other. It's a crucial factor because it directly impacts how well the fuel burns. When we talk about combustion, the goal is to find that sweet spot in packing the fuel. Not too loose, not too tight. If the fuel is too loosely packed, oxygen can easily reach the flame zone, which is great for maintaining good combustion. But if it's packed too tightly, it can restrict airflow and reduce combustion efficiency. On the other hand, if it's too dense, heat transfer becomes less efficient, which can hinder the overall burning process. So the key is to achieve a balance, enough space for oxygen to flow freely, but also enough density to transfer heat effectively. This balance is essential for optimizing combustion, which, as you know, is a core part of efficient energy release in our systems. Understanding and controlling fuel compaction helps us improve performance and efficiency across the board. Fuel moisture is typically expressed on a dry mass basis, meaning we're looking at the amount of water in the fuel relative to its dry weight. This is a critical factor because it directly influences the fire's behavior. When fuel is moist, it tends to be harder to ignite, and the fire's intensity can be significantly affected. Moisture also impacts how much fuel is consumed and how quickly the fire burns. One of the most important effects of moisture is its smothering action. Water vapor leaves the fuel as it heats up, creating a kind of barrier that makes it more difficult for the fire to spread. Additionally, this vapor dilutes the oxygen around the fuel, which is essential for combustion. So, in essence, moisture acts as a natural suppressant, making it a key element to monitor when assessing fire risk and behavior. Understanding this helps us better predict and manage wildfires effectively. Let's talk about fuel load. Essentially, this refers to the amount of combustible material available in a given area. Now, fire intensity is closely linked to this because it's directly proportional to the amount of fuel present. In simple terms, the more fuel there is, the more intense the fire can become, assuming the fire spreads at the same rate. This means that when we're assessing fire behavior, understanding how much fuel is available helps us predict how fierce the fire might get. It's a crucial point because managing fuel loads can significantly influence fire control efforts. So, in the broader context of fire behavior, fuel load is a key factor that determines how severe a fire can become at any given moment. Let's take a closer look at some of the atmospheric and physiographic conditions that play a crucial role in our subject. First, air temperature is a key factor because it influences many processes, from weather patterns to how materials behave in the environment. Higher temperatures can accelerate certain reactions or processes, while cooler conditions might slow them down. Next, we have relative humidity, which tells us how much moisture is in the air compared to what it could hold at a given temperature. This is important because it affects evaporation rates, plant growth, and even the stability of certain landforms. Wind is another significant element. It can shape landscapes by eroding surfaces or transporting particles over distances. Wind also impacts drying times and can influence the spread of weather systems. Then there's slope, which is essentially the incline of the land. The steepness of a slope affects water runoff, erosion potential, and how easily materials can be transported or deposited. All of these factors, air temperature, relative humidity, wind, and slope, interconnect and influence one another. Understanding these conditions helps us better grasp the overall environment and how it might change or respond to various influences. They form the foundation for many of the processes we've been discussing and are essential for a comprehensive view of the landscape dynamics. Let's talk about how air temperature directly impacts fire behavior. Essentially, it influences the temperature of the fuel, which is a crucial factor in how fires develop and spread. When the air temperature is relatively moderate, fires tend to be safer. In fact, fires are generally considered manageable when their energy release is at or below 3,500 kilojoules per second per meter. To put that into perspective, maintaining air temperatures below around 30 degrees Celsius helps keep fire behavior within safer limits. So, understanding and monitoring air temperature is vital for predicting fire behavior and ensuring safety during firefighting operations. Let's talk about relative humidity and how it affects fire behavior. The relative humidity of the atmosphere plays a significant role in determining the moisture content of the fuel. When the air is more humid, it adds moisture to the fuel, which can actually reduce the fire's intensity. This is especially true when the fuel moisture content drops below 40%. Practical experience has shown us that when the relative humidity is at or below 30%, the potential for a fire to become intense increases considerably. Lower humidity means less moisture in the fuel, making it easier for the fire to spread and burn more fiercely. Understanding this relationship helps us predict fire behavior more accurately and plan our responses accordingly. So, in summary, as relative humidity decreases, especially below 30%, the risk of high-intensity fires increases, which is a critical factor to keep in mind during fire management. Now, let's talk about the role of wind in fire behavior. The combustion rate of a fire is directly influenced by how much oxygen is supplied to it, and wind plays a key role here. When the wind increases, it supplies more oxygen, which can make the fire burn faster. Additionally, wind affects the shape of the flames. It causes the flames to become more acute in their angle, meaning they lean or tilt in the direction of the wind. When wind velocities are high enough, they can actually push the flames into unburned material ahead of the fire, potentially spreading it more quickly. Another interesting point is that flame height tends to decrease as wind speed increases. So, in windy conditions, flames might be shorter, but the fire can still spread rapidly because the wind helps carry embers and preheat unburned areas. Overall, wind is a critical factor in fire behavior, influencing how quickly a fire spreads, how intense it appears, and how it interacts with the environment. Understanding this helps us better anticipate fire movements and improve our response strategies. Let's talk about how slope affects fire spread. When a fire burns up a slope, it can actually increase the rate at which the flames move forward. This happens because the slope causes the unburned fuel in front of the fire to preheat more quickly, making it easier for the fire to spread. On the other hand, if the fire is burning downhill, the rate of spread tends to decrease. The fire doesn't advance as rapidly because the preheating effect is less pronounced downhill. Now, a key point to remember is how dramatically the slope angle impacts fire speed. For example, when moving from a moderate slope of 0 to 22 degrees, the rate of spread doubles. If you increase that to a steep slope of 22 to 35 degrees, it doubles again. And on very steep slopes, from 35 to 45 degrees, the spread doubles yet again. This shows just how influential slope can be in fire behavior, and understanding this helps us better predict and manage fire spread in different terrains. It's a crucial piece of the puzzle when considering fire dynamics and overall wildfire behavior. Now, let's look at the relationship between the slope and the rate of spread. The formula we're using here is R equals rho times E to the power of B times. What this means is that the rate of spread, R, depends on the original rate on level ground, rho, adjusted by an exponential factor. The constant B is 0.0693, which has been determined through empirical data. The variable x represents the angle of the slope in degrees. In essence, as the slope angle increases, the rate of spread increases exponentially. This highlights how steeper slopes can significantly accelerate the spread, which is a crucial point when assessing fire behavior in hilly or mountainous terrains. Understanding this relationship helps us predict how fires might behave differently depending on terrain, reinforcing the importance of considering topography in fire management and safety planning. When it comes to using fire behavior data in ecosystem management strategies, one key point is that controlled burns should ideally be applied as head fires. This approach tends to cause the least damage to the grass sward, which is often a primary concern. At the same time, head fires can be quite effective at targeting woody vegetation, allowing us to manage that aspect if necessary. Now, when we're burning to remove dead or unacceptable grass material, it's important to keep the fire at a low intensity. This helps us remove the unwanted material while minimizing damage to the healthy grass. Achieving this low-intensity burn depends on specific conditions. Mainly, doing it when the air temperature is below 20 degrees Celsius and the relative humidity is above 50%. By paying attention to these weather conditions, we can ensure that our burns are both effective and environmentally responsible. This approach aligns with our overall goal of managing ecosystems sustainably, using data-driven decisions to balance fire's benefits and risks. When we're aiming to eradicate or prevent the encroachment of undesirable plants through burning, it's important to recognize that an intense fire is usually required. Now, when dealing with herbaceous species that are encroaching, these plants are typically highly flammable themselves. This means that the amount of grass fuel needed to destroy these herbaceous plants is actually less than what we would need to destroy tropical and subtropical trees and shrubs, which often have non-flammable foliage. Research and practical experience tell us that a fire intense enough to destroy the aerial parts of a bush up to around 2 meters in height can be achieved. This is a key point because it highlights the importance of fire intensity and how it relates to the target vegetation's structure and flammability. Overall, understanding these differences in plant flammability and fuel loads helps us plan more effective fire management strategies, ensuring we use the right intensity to achieve our goals, whether it's clearing out undesirable plants or managing encroachment, while maintaining safety and ecological balance.